So this is about deep learning architecture. So the first talk will be given by Yuzha Lee. The title is Graph Matching Networks for Learning the Similarity of Graph Structured Objects.
I'm Yuzha Lee from DeepMind. Today I'm presenting our work on graph matching networks for learning the similarity of graph structured objects. So graph structured data appear in many domains. They can be, for example, used to model molecules. They can be used to represent images as scene graphs of objects and relations. They can also be used to represent programs using their semantic or syntactic relationships between the expressions or statements of your source code, and they can also be used to represent software binaries as control flow graphs. This kind of graph structured data are used in many different important applications. In drug discovery, for example, we might want to search over a library for molecules or drug candidates based on some notion of similarity between the molecules. In image retrieval, if we use the scene graphs, we can find semantically similar graphs, similar images, rather than only visually similar images. For programs, if we analyze the program graphs, we might do better in code search. And for computer binaries, if we analyze the structure and the semantics of the control flow graphs and search within a library of binaries with known issues, we might be able to identify vulnerabilities of our software. Across all of those applications, there's one common problem of finding similar graphs under some notion of similarity, typically from a database of graphs. And this is a very highly challenging task because the graph structures vary a lot from instance to instance and also from problem to problem. In this problem, the nodes and edges can also have attributes. Therefore, we need to not only reason about the topology, but also reason about the semantics of the graph structure. And also, the notion of graph similarity varies a lot from problem to problem. And ideally, we want an algorithm or model that can automatically adapt to different notions of similarity, and also to without changing the algorithm or model itself. The binary function similarity search problem is what motivated us to study graph similarity learning, and it started as a collaboration with a security expert in Google. In this setting, the goal is to check, given an incoming binary, if it contains any vulnerabilities that can be exploited. And in this case, the first thing we typically do is to analyze the incoming binary using some static binary analysis to convert the binary into assembly code, and then from the assembly code, reconstruct a control flow graph out of it. And this control flow graph contains all the structural and semantic information about the binary. In our analysis, we focus at the function level, but a program software can contain many, many functions. This is a very simple example where the code contains only a function with an if-else statement, and you can clearly see the two branches in this computation, in this control flow graph. But in our experiments and in our project, we use graphs that have sizes of vastly different sizes, from tens of nodes to thousands of nodes. And once we converted the binaries into such control flow graphs, the problem becomes a search in a library of binaries with known vulnerability issues. And the task would be to identify if the incoming query graph are similar enough to any of those candidates in the library. And if so, this query binary might contain similar vulnerabilities as the candidate matches. And then we can notify the author of the program such that they can apply patches quickly. However, the similarity between those control flow graphs is a highly non-trivial task because a single change on the graph structure or on the nodes can make the control flow graph be completely different in a semantic sense. And also, not only does the graph structure matter, the nodes themselves might also contain useful information like the assembly code that describes what computation the code is actually doing. So this task requires us to jointly reason about both the graph structure and the graph semantics. Most existing approaches on estimating graph similarity are based on hand-engineered algorithms or heuristics with only limited amount of learning. Most notably, one approach is based on graph hashes that maps each graph into a descriptor through some human-designed hash functions that encode the graph structure. So this is actually an approach that is widely used in the security applications. And this approach is very good at finding exact matches, but not so good at finding similar graphs. Another notable approach is the graph kernels, which takes a pair of graphs as input and then compute a similarity score on the pair of graphs jointly through some human-designed kernels and computation processes. And this approach is very popular in various graph-level prediction tasks like graph classification. We frame these two paradigms as graph embedding and graph matching. In the graph embedding approach, a graph is mapped to a descriptor independent of any other graph. And therefore, this makes this approach very efficient in terms of computing both the descriptor as well as doing retrieval, because we can utilize efficient retrieval data structures like hashing. On the other side, the graph matching approach computes a distance or similarity between a pair of graphs jointly, and therefore might be more expensive in terms of computation, but it can use that extra computation to improve the accuracy of graph similarity estimation. We aim to learn a graph similarity or distance function on a pair of graphs in this project. And we want this distance function to behave in a way such that similar graphs have a small distance and dissimilar graphs have large distance. We can learn such a distance function using supervised learning on labeled pairs and triplets. With labeled pairs, we assume that each pair of graphs is labeled either as similar or not similar, and each triplet is labeled in a way such that the graph 1 and graph 2 in each triplet are similar, and graph 1 and graph 3 in each triplet are not similar. With supervised data like this, we can use a pretty standard margin-based loss to train the distance function such that it behaves in a desired way. The most important part in the graph embedding approach is the graph embedding function itself. Based on the recent success of the graph neural network models, we structure our graph embedding function using those graph neural nets. And more concretely, the embedding function has two parts. The first part is a message passing part that computes node representations of a graph. And these node representations encode structure and semantic information within local neighborhoods around each graph. And then after we get those node representations, they're aggregated over the graph to compute a graph-level representation. And these graph representations are then used as the embeddings and feed into the distance functions. Within the message passing part, it iterates over two steps. The first step computes the messages along each of the edges in the graph based on the representations of the nodes associated with that edge, as well as an edge attribute vector if those are available. And after you computed all the messages on the graph, each node would aggregate over all the incoming edges and then update its own representation through a node update module, which could be a feed-forward neural network or a recurrent neural network core like GRUs or LSTMs. And this message passing process is iterated for a few number of steps. And after that, each node would have the representation that capture a local neighborhood. These node representations are then aggregated across the graph through a pooling operator. And then these pooled representations are passed through a feed-forward neural network to further transform that into graph embeddings. In this aggregation module, the pooling operator can be as simple as a sum function, but it can also be something more expressive as a attention-based pooling. And this embedding model can be directly plugged into the distance function and the margin-based loss, and we can train the whole thing end-to-end through gradient-based training. So that is the graph embedding approach. Our graph matching networks, on the other hand, computes the representations of a pair of graphs jointly, which, as I have mentioned before, can, in some sense, be more expensive in terms of computation, but it can be more accurate in terms of estimating graph similarity. And the model itself is very similar to the graph embedding approach. And the only difference is that within each message passing round, each node would not only get messages within the same graph, but also attend to all the nodes in the other graph through an attention mechanism. We utilize a similarity score between each pair of nodes across graphs. And this similarity score can be computed, for example, through the popular dot product similarity or some Euclidean similarity functions. And then we compute an attention score, which is a softmax over all the similarity scores. And then the cross-graph messages between each pair of nodes is computed as the difference of the node representation vectors weighted by the attention weight. This kind of cross-graph attention mechanism has a very interesting property. If we look at the total cross-graph message coming into one particular node, then it has this particular form that is actually the difference between the representation of that node and an attention-weighted average of all the nodes, all the node vectors from the other graph. So effectively, it is matching that particular node to the closest node in the other graph, and then take the difference between their representations. So that is also why we call our approach the graph matching networks approach. And this approach has an interesting property that if the two graphs are actually identical, and if the attention map concentrates on the best match, then this cross-graph message is actually a zero vector. And that means in future rounds of message passing, the two graphs would continue to compute identical node representations because of those messages are zero. And on the other hand, if the two graphs are not identical, then this cross-graph message would contain important information about the difference between the graphs, and the model would be more sensitive to all sorts of differences. And after all these kind of messages are computed, each node would update its own representation by incorporating both the in-graph as well as the cross-graph messages. There are a few other possible variants of our model. For example, instead of using the particular graph neural network architecture we presented here, we can use other popular architectures like the graph convolutional networks. And also, in addition to relying on a pre-specified distance metric like Euclidean or Hamming distance, we can use a Siamese network architecture to use a neural network to directly predict a similarity score. Compared to the graph matching approach, the Siamese networks actually combines the information between the two graphs at the very end of the model. But the graph matching model we presented here merges the information of the two graphs at the very beginning of the model. And in experiments, we'll show that the matching approach consistently outperforms these other two approaches. We present experiments in 3 different domains. The first is a synthetic task where we learn graph edit distances on synthetic graphs. And in this task, we treat graphs with small edit distance to be similar and graphs with large edit distance to be not similar. And the second domain is the control flow graph-based binary function similarity search that I presented before. And in this case, our data comes from compiling the popular open source video processing software FFmpeg with different compilers and different optimization levels. And here, the binaries corresponding to the same source function are treated as similar. But this similarity between the control flow graphs is actually a very tricky one, because even for the same function, if you compile it with different compilers and different compilation optimization levels, the control flow graphs can have very different topology and very different sizes even. The third domain is a mesh graph retrieval domain, where we have mesh graphs from 100 different object classes. And we treat the graphs for the same object class as similar, and graphs for the different object classes as not similar. On the synthetic task of learning graph edit distance, we train and evaluate on graphs of different sizes and different edge densities, and measure both the pair classification AUC as well as the triplet prediction accuracy as the metrics. And we use the popular Weisfeiler-Lehmann kernel as our baseline. From the experiment results, we can clearly see that the learned models do better than the WL kernel on this kind of data. And also, the matching model performs consistently better than the embedding model. On the binary function similarity search task, we compare the graph neural network embedding approach and the matching networks with a hand-engineered baseline, which relies on doing jointly the graph hashing as well as locality-sensitive hashing, which is actually a popular and effective approach used in many security applications. We also explore along the dimension of using the graph structure only versus jointly using both the structure and the feature on the graphs. From the experiment results, we can draw 4 different conclusions. First of all, the learned approaches are consistently better than hand-engineered solutions if we run the message passing on the graphs for enough number of rounds, such that the learned representations contain enough structural and semantic information about the graph. And also, the matching model is consistently better than doing embedding alone. Joint modeling of the structure and the features is better than modeling structure alone. And lastly, the performance of the graph neural network approaches gets better with more and more graph propagation and message passing steps because it more efficiently utilizes the graph structure. We did more ablation studies on the function similarity search as well as the matched graph retrieval tasks. And the experiment results show that the graph matching networks consistently do better than all the other alternatives. And in particular, they're better than the Siamese network architectures, which shows that it is beneficial to merge the information of 2 graphs early on in the model rather than only doing it at the very end. There's one nice thing about our model is that we never supervise the cross-graph attention patterns. But after learning, our model still figures out that there's something interesting going on those attention patterns. And if we visualize them, we can see that it demonstrates some interesting behavior. So this is a model learned on the graph edit distance task. And after learning, we apply it to this particular example where it is a pair of graphs that are identical. And you can see that the attention pattern converged to almost a node-to-node mapping. And in this particular case, because of some in-graph symmetry, each node actually identifies 2 equally good matches. On the other hand, if the 2 graphs are not identical, then the attention pattern is less interpretable. But still, the attention pattern is pretty sparse, and it demonstrates some interesting behaviors. So to conclude, I hope I've convinced you that graph similarity can be learned through graph neural networks. And the learned graph embedding model are very good and efficient for this kind of tasks, and the graph matching networks are even better. There are many different future directions we could explore. One obvious one is to make the cross-graph attention and matching more efficient. And the other, probably more exciting direction is to explore new deep learning architectures that can utilize this new capability of learned graph similarity. So with that, I'll conclude and happy to answer any questions.
Any questions? So I have one question. So how slow is your graph matching network compared to the baseline?
Yes, that's a very good question. Because the graph matching networks, because it does this pairwise node matching across the graph, so it is actually quadratic in graph size in each message passing round. But the embedding model is actually linear in terms of computation in each message passing round. So it is more expensive than the graph embedding model. So in a real retrieval setup, what we would recommend to do is to use the graph embedding model as a cheap way to embed and then hash the graphs to do a fast filtering of the graphs. And then once you retrieve a small set of candidates, you can use these graph matching networks to refine the retrieval results and to get higher quality. So yeah, because this model, we think it provides a nice trade-off between computation and accuracy, and we can explore different ways to trade this off.
Thank you. Okay, so let's thank the speaker. So we will do 5-minute presentations. I believe the first talk, there is no authors available due to some visa issues. So I'll try to play the video instead.
Hello everyone, my name is Hongpeng Zhou. It's a great honor for me to present our work on neural architecture search. I come from the Delft University of Technology. It's really a shame that we can't attend the conference due to the US visa issues. I will introduce our study from 5 aspects. First is the highlight of this paper. The first feature is fast. We find the architecture on CIFAR10 within only 0.2 GPU days using a single GPU. The second feature is simple. We train network for only one epoch. Thirdly is the first Bayesian method for one-shot NAS. A fast hashing calculation method is also proposed. Finally, we design search space. We also consider dependencies between nodes, which ensures a connected graph. But why we do research on these aspects? Firstly, why we use one-shot method? Because compared with other frameworks, the one-shot approach could reduce search time without separate training and treats NAS as a network compression on the architecture parameters. While we use Bayesian learning, research had shown that the Bayesian learning had some advantages. First, it could prevent overfitting without tuning lateral parameters. Second, we could model architecture parameter using hierarchical pairs. Thirdly, they can promote sparsity and model dependency between nodes. For the Laplace approximation, which is a deterministic method for Bayesian learning, it's simple for implementation. It also uses hash information, which has a close relation to compression and could accelerate convergence. When designing search space, we found that most one-shot methods disregard dependency between nodes, which may result in disconnected graph. For example, in the red figure, if node 2 is redundant, then the edge 24 and edge 23 should be deleted. However, they may still retain if the dependency is disregarded. How to realize the highlights we mentioned before. For dependency, we propose a multi-input, multi-output motif, which is a basic block for any partial network. The red two figures stand for the motif. We also give proposition to explain what dependency is. Look at the motif. If there exists information flow from node J to K, at least one parenthesis edge from I to J should be non-zero, and at least one connection from J to K is also non-zero. In fact, this proposition tells the parenthesis edge should have superior control over its successors, such as subfigure A. If parenthesis edge 1, 2 is redundant, then the successor edge 2, 3 and edge 2, 4 should also be removed. To realize this, we design switch to each edge. As you see in subfigure B, the S stands for uncertainty, which could be explained by Bayesian learning. For the Bayesian strategy, we assume the pairs at Gaussian distribution, which should consider dependency between nodes. The cost function is the maximum likelihood with regularization. It consists of 3 parts: the loss on data, the regularization on architecture parameter, and the network parameter. In addition, we also develop efficient hashing calculation method by converting the convolutional layers into fully connected layer. As a byproduct, our approach can also be used for network compression directly. Sparse models can be obtained without accuracy loss. To prove our method, we did experiments on 2 datasets, CIFAR10 and ImageNet. On CIFAR10, we did both proxy and proxy-less experiments. The best convolutional cells and passes are searched in a complete network. These 2 figures are the optimal structure we found. Table 1 shows the compression result. Our method is competitive with less search time. The transferability is proved on ImageNet. The result showed we could also achieve competitive performance. With the previous result, we draw the conclusion. First, our method is a first Bayesian approach for one-shot NAS. Then the search is simple and fast. Thirdly, we could further reduce search time by computing hashing with backpropagation. We know that our result is not state-far due to application techniques. If you have any ideas about how to improve it, please contact us. Thank you.
Can the next speaker come to the podium? So the next talk is Set Transformer, a framework for attention-based permutation invariant neural networks. And the authors are Juho Lee, Yoonho Lee, Jungtae Kim, Adam Kosirek, Sungjin Choi, and Yue Tae.
Okay. Hello, everyone. I'm Jungtae Kim from Postec. Today, I'm presenting a set transformer, which is a framework for attention-based permutation invariant neural networks. This is a joint work with Juho Lee, Yoonho Lee, and Adam Kosirek, and Sungjin Choi, and Yue Tae. So the problem we want to solve is set input problems. So it means these problems take sets as inputs. So it means the inputs have variable lengths, and the order does not matter. So the application of these problems are multiple instance learning, point cloud classification, and feature image classification. So the one of the previous work is deep set network, which is a simple way to construct permutation invariant set input neural networks. But as shown in the equation below, it does not effectively modeling interactions between elements in sets. So a deep set is some aggregation, simple sum aggregation of feature vectors produced by some multi-layer perceptrons. So it cannot model interactions between elements in sets. So we propose the attention-based set operations. We use multi-head self-attention to encode interactions between elements in a set. There are 3 runnable parameters in multi-head attention, WQ, WK, and WV. So if 2 arguments are same, X and Y are same, it can be worked with as a self-attention network. So, and then the one property of self-attention is permutation equivariant, which means self-attention of permute of X is equal to permute of self-attention of X. So this is the basic blocks which are used in building an encoder of set transformer. So multi-head attention block has residual connection and multi-head QKV attention followed by a feed-forward neural network. And then, as I said before, a self-attention block, SEP block, is built in self-attention way. But the complexity of this SEP block is over n squared. So we propose the more efficient version of SEP block. So that is induced self-attention block, ICEP. So it has a set of trainable inducing points to simulate self-attention. So this, the complexity of this ICEP block is over n m with m inducing points. Okay, so yeah, okay. And then the basic block, which is used in the decoder of set transformer, is PMA, pooling by multi-head attention. So instead of a simple sum max mean aggregation, we use multi-head attention to aggregate features into a single vector. But we can also use multiple seed vectors, so we can apply self-attention to produce multiple interacting outputs, like O. Yeah, so this O is matrix, so yeah, this is K vectors. So here is the overall architecture of set transformer. So encoder is a stacks of permutation equivariant ICEP blocks. So for example, there are L stacks of ICEP blocks. So G is the output of encoder, and then G is input to the decoder. So a decoder is PMA followed by self-attention to produce outputs. So the seed vectors are passed through PMA, and then the output of it is passed through L SEP blocks, for example. So here is one of the experiments, amortized clustering, which attempts to run a mapping from data set clustering. So deep set network does not work well in these problem, but our method, our set transformer works well in this problem. So we demonstrate that our method works well in various tasks such as unique character counting, amortized clustering, point cloud classification, and anomaly detection. And we show that our method generalizes well with a small number of inducing points, and by ablation study, attention both in encoder and decoder are important for the performance. So here is the conclusion. So we propose use set input neural network architecture, and it can efficiently model pairwise and high-order interactions between elements in sets. And we demonstrate that our method works well in various set input tasks, and our codes are available in this GitHub repository. Thank you. Thank you for listening, and please stop by our poster. Thank you.
Okay. Hello, everyone. My name is Yiğitcan Kaya. Today I will talk about overthinking. I'd like to thank my co-author Sang-Yin Hong and my advisor Tudor, who is here. Okay, let's start. I'm sure every grad student in this room knows exactly what overthinking is. So overthinking basically is thinking more than needed to solve a problem. And what does this do? One, this wastes our valuable energy, and two, this causes us to make avoidable mistakes. So in this paper, we ask, do deep neural networks overthink too? So it turns out they do, like grad students. So, and we find that without requiring the full depth, DNNs can correctly classify the majority of samples. And what does this do? This wastes computation for up to 95% of the samples. And two, this occurs in 50% of all misclassifications, so it is very destructive. So the question is, how do we detect overthinking? So we introduced this notion of internal classifiers that allow us to observe whether the DNN correctly classifies the sample at an earlier layer. And we do this through our generic modification, which we call shell of deep networks, or SDM for short, which introduces the internal classifiers. So here we see a sketch of our, simple sketch of our modification. Like there we have a 5-layer convolutional neural network. We introduce an internal classifier after the second layer. And this internal classifier produces an internal prediction. And we see that like, in this example, there is only one internal classifier, but we can introduce more than one. So the first challenge is, how do we train accurate internal classifiers? Here, prior work claims that this hurts the accuracy of off-the-shelf deep neural networks, and the prior work proposed a unique, not generic architecture. But our results show that our modification often improves the original accuracy by up to 10%. So here we see like a sketch of the wasteful effect of overthinking. We have this nice image of a horse, which is correctly classified in the internal classifier as a horse, so which makes the layers after the internal classifier wasteful for the correct classification. So the challenge, how can we know where in the DNN to stop? So our solution is very simple. We simply use classification confidence of the internal classifiers. And it turns out our confidence-based early exit scheme reduces the average inference cost by up to 50%. Now let's talk about the destructive effect of overthinking. We have this another image of a nice horse, which is correctly classified as a horse in the internal classifier, but in the final classifier, it is misclassified as a dog. So the layers after the internal classifier are destructive for the correct classification. And as you can see, there's a disagreement between the internal classifier and the final classifier. So the challenge here, how can we quantify this internal disagreement? And our solution is the confusion metric. So we designed the confusion metric, and our metric indicates whether a misclassification is likely, so which makes it a reliable error indicator. Also, interestingly, it turns out that backdoor attacks also increase the confusion of the victim network on malicious samples. So what are the implications of all this? First, we see that eliminating overthinking would lead to a significant boost in accuracy and inference time. And second, we need DNNs that can adjust their complexity on the fly based on the required feature complexity. And this would eliminate, hopefully eliminate overthinking. And for more details, we set up a nice website, shallowdeep.network. Please see that. And come and see our poster. We have the poster number 24. And I thank you for listening.
Hi, I'm Hong Yang. So today I'm going to present my work, GraphUNet. This work is done with my advisor, Dr. Xuewang Ji from Texas A&M University. Image and graph are very similar in several aspects. So image can be treated as a spatial graph with well-defined locality. But on graph, there is no such kind of locality information. So it is hard to define the corresponding pooling and unpooling operations on graph data. Also, the node classification problems can also be considered as image segmentation problems. Both of them make predictions for each node and each pixels. From this observation, so we want to use the methods from image segmentation to solve the node classification problems. So UNet is a very popular network architecture to solve the image segmentation. So we want to define a UNet on graph data. The key component of the UNet include the convolutional layer, pooling layer, and unpooling layer. But on graph, we only have GCN layers. So the definition of pooling layer and unpooling layer is not clear on the graph data. So in this work, we propose the graph pooling layer and the graph unpooling layer, and based on them, we propose the graph UNets. So this is our graph pooling layer. So the input graph is represented by two matrices. One is the adjacent matrix, and another one is the feature matrices. So each row in the XL corresponding to one node feature. And we use an trainable projection vector. So we project each node's vector to the projection vector and get the projection score, which is stored in Y. And we select the nodes with the largest K projection values and store the index of them in the IDX. So we extract the corresponding nodes to form the new graph. Also, we use the gate operation to control the information flow. The output of the layer is XL+1 and AL+1. Then we define the graph unpooling layer. So we use the idea of the unpooling layers on images. The graph pooling layer will output the sampled graph and also the position information. Then the graph unpooling layer can use the position information to reconstruct the original graph structure. Based on these two layers, now we can define the graph UNet. So the left part is the encoder part, and the right part is the decoder part. And we add some skip connections between them. We evaluate our methods on node classification tasks and the graph classification tasks. So both of them demonstrate that our methods are very effective. So if you are interested, please come to poster number 25 for more details. Thank you.
So, need to move this down and switch the there should be a switch here to switch number 1 and number 2. 1 dBi, I guess. Okay. Let me sneakily move my snow here and zoom the. Okay.
Can I do some introduction?
Sure.
Okay, so the next talk is SetNet, Bridging Deep Learning and Logical Reasoning Using a Differentiable Satisfiability Solver. The authors are Po-Wei Wang, Priya Donti, Brian Wilder, and Zico Coulter. And I'd like to mention that this paper got the Best Paper Honorable Mention Award. So here's your
Thank you.
award. Yeah. And yes, congratulations.
Hello, I'm Paul Wei. Today I'm going to present our work, SetNet. We show how to incorporate a differentiable set solver into a deep learning system. This allowed us to bridge two apparently opposed views of the world, deep learning and logical reasoning. This is a joint work with Priya Donti, Brian Wilder, and my advisor, Zico Coulter. There were once two opposing views about modeling. First, the deep learning way, in which you put your input in some feed-forward or recurrent function that has a lot of representational power. The model is continuous and differentiable, but there is usually no way to impose constraints on the output. We usually solve this problem using some kind of gradient optimizers. Second, the logical inference way, which can solve discrete constraint problem when the constraints are known. It deals with discrete variables, and as a result, is inherently non-differentiable. These problems are usually solved via a tree search approach. These two views of the world, the deep learning view and the logical inference view, have different strengths and weaknesses. For example, say that we want to solve the Sudoku problem in today's newspaper. One way to solve this problem is to use a convolution network to identify the digit, feed the result into a set solver that knows the constraint governing Sudoku, and solve the answer. But doing so requires some non-prior about the Sudoku puzzle, that is, knowing all the rules about the game beforehand. So what if we are in a different setting where we don't know the structure of the problem or the rule about the game? But we do have the data about Sudoku puzzle and their associated solutions. It might be natural to wonder if we can simply plug the set solver into the deep learning system to help us learn the constraint and the solution in an end-to-end fashion. This leads to two questions. Number one, can we integrate set solvers into deep learning systems? In other words, can we backpropagate through these solvers? Number two, can doing so allow us to learn the constraint of the set solver purely from data? The answer to both of these questions is yes. We will present a differentiable set solver that learns both the constraints and the solutions solely from examples. Now, before showing about what this talk is about, let's first show what it is not. This talk is not about using a neural network to find a set solution, but about learning both set constraint and solution from examples. That is, we do not assume any given rule and structure. Also, this talk is not about simply using a deep learning and set solving in a multi-stage manner, because doing so requires prior knowledge about the structure and constraint, which we might not have. Further, current set solver cannot accept probability input from the neural net. Thus, they cannot be plugged into the architecture directly, not even mentioning backpropagation. This talk is about a differentiable layer that enables end-to-end learning of both constraint and solution of logic problems. All learning is done solely from examples. And we will present a smooth, differentiable MaxSet solver that can be integrated into a loop of deep learning systems. Let's first briefly review the set problem. We are given a collection of Boolean formula, and the goal of the set solver is to find some assignment to this variable v to satisfy all the clauses. We can encode this using a clause matrix S that has a row for each of the clauses and a column for each of the variables. And the sign in the matrix defined in the clause actually is a set problem. Now, in a normal set setting, we are given the closed matrix S, and our goal is to find a satisfying solution. But in our setting, however, the closed matrix will be the parameter of the layer, and we will need to learn them. In practice, we are going to use an optimization variant of set problem, the max set problem. In a set problem, we either find a feasible variable assignment satisfying all the constraints or claim that it's not feasible. But in the max set variant, we want to maximize the number of satisfier clauses, even if it is not totally satisfiable. It is known that both set and max set are NP hard because they are doing discrete optimization on binary variables. One way to make the problem smoother and easier is to relax the binary variable by lifting it to a smooth and continuous sphere. The binary constraint on the variable vi is actually equivalent to the absolute value constraint on a real line, which will result in the discrete set +1 and -1. If we relax the variable into a higher dimensional space, the constraint will become smoother, and the problem will be easier. The relaxation is equivalent to the semi-definite program proposed by Gomez and Williamson in 1995, in which they optimize on the covariance matrix X of V. The SDP relaxation has strong theoretical guarantee and is solvable in polynomial time. Here, we propose SetNet, which uses the max set SDP relaxation as a layer and can be plugged into the loop of deep learning systems. This layer takes the assignment of set variable as input and output and has a learnable weight, the closed matrix S. At this point, you might be wondering through. Deep learning networks are continuous, which means that the input of the layer are continuous. However, I mentioned earlier that most set solvers cannot accept probabilistic or continuous input. Fortunately, this is not the case for SDP, which operates in the continuous spherical space. Before feeding the data into SDP, we need to first transform the probability input from the neural net into the spherical space that the SDP solver can handle. Specifically, for each of the probability input, we relax it onto a unit sphere by a random projection. This way, we can feed all the non-relaxed input into the SDP relaxation and solve it via an SDP solver. Given the solution from the SDP, we can again run it back to the probability space and output the probability for each of the variables that we are solving for. However, there's one serious problem. The SDP is too slow to solve, even if it is in polynomial time. Traditional solvers use variant of the primal dual entry point method, which take n to the 6th time to solve the max set SDP. This is too expensive and won't scale beyond hundreds of variables. Fortunately, we have the secret weapon, a fast algorithm to solve the max set SDP. When all the constraint of the SDP is diagonal, like in our case, the problem can be efficiently solved by a low-rank factorization over the X matrix called the Burr-Monteiro method. The details of this equation aren't too important, but the key element to highlight here is that there is a very efficient gradient descent formulation with simple closed form. We can solve the factorization V column by column to greedily optimize the low-rank SDP. For a sufficiently large K that is the dimension of the unit sphere, the optimization procedure converges to the global optimum of the SDP, despite the formulation now is non-convex. We proved this concurrently with another team at MIT. In conclusion, the complexity of solving the SDP reduced from n to the 6th to n to the 1.5 times m, where the m is the number of clauses that is usually less than n in our settings. Now we have the efficient optimization procedure to solve the SDP relaxation in the forward path. But how could we backprop through the optimization procedure? Actually, it's not very hard. When the block coordinate descent procedure converge, it will satisfy the following fixed point equation. The fixed point equation will provide an implicit function characterization of the solution V and its parameter S, which we can differentiate through. Thus, after applying the implicit function theorem, we will have the following equation by chain rule. The equation will form a system that is linear to the gradient of V with respect to S. And we can solve the above linear system to get the gradient we need for backprop. The linear equation can actually also be solved efficiently via a block gradient descent. Okay, to recap, up until now, we have explained how our smooth differentiable set solver works. In the floor path, it takes the probability input, project it into a relaxed sphere, solve the max set SDP using this relaxed input, and yield relaxed output, which will round back to probability. The weight of our layer is as the parameter of the max set SDP. In the backward path, we will differentiate through the SDP solution procedure of block gradient descent using the implicit function differentiation. This is a key contribution of our work, actually. In practice, there are additional ingredients that are important to be aware to make the SATnet work. For example, we can train the closed matrix S to be low rank to regularize in the training procedure. The reason for the regularization is that there are actually doubly exponentially many possible Boolean functions considering the input and output of the set solver. We usually prefer simpler functionals which can be implemented by fewer set clauses to prevent the overfitting. The low rank regularization on the S matrix actually corresponding to regularizing the number of clauses in the set problem. And another important ingredient we haven't mentioned is the auxiliary variables, that is, the hidden node. By adding auxiliary variables, that is, the get they call in theoretical computer science, they are able to increase the representational power of the diagonal SDP relaxation. Now, I'd like to show some experiments to illustrate how the SATnet works. The first example is about learning the parity function from a single bit supervision. Although the idea of parity is easy, just figure out whether you have seen an even or odd number of ones. We know that the parity function is hard for most deep networks to learn. I'm going to show that for a sequence of length 40, the recurrent chain SATnet can actually learn the parity function easily from 10K examples, while the LSTM will struggle to learn it. This is because the parity function is expressible via SAT, and the low-rank regularization of SATnet can train those possible Boolean function space. The next experiment I'd like to show is learning Sudoku solely from example. I'm not talking about solving it given a rule, since that is quite easy, but about learning both the constraint and the solution given the training data about unsolved and solved puzzle as supervision. We'll first feed the SATnet with 10K example in a bit format, which means that we don't tell the SATnet anything about the structure of the cell, such as localities. In the case of SATnet layer, the parameter we are learning here is the closed matrix S. Finding a correct S will correspond to creating a set instance that represents the rule of the game of Sudoku. We found that with this method, we are basically able to learn, with very few mistakes, how to place Sudoku on both the training and testing set, just from examples and given no information about the problem. The ConvNet, in contrast, do not do well at all on this small number of examples. Even better, we find that the SATnet can not only learn Sudoku, but also a permuted version of Sudoku in which we permute the bit input. ConvNet utterly failed at this case because they rely on the locality structure of the bits. But the permutive version has no notation of locality anymore. Human can solve the permutive version either because the board looks nonsensical. However, SANet can still solve the permutive Sudoku because the notation of logical input does not change between the original and the permutive settings. As a final example, I want to come back to the motivating example I gave, learning how to solve a Sudoku given a picture of the board. In this case, our picture of the board is an MIT version of Sudoku, where each Sudoku digit is an MIC digit, and the blanks are zeros. In our solution procedure, we'll do the following. We first apply a convnet to each of the digits. We feed the result clarification into a SANet layer and apply a loss on the subsequent output. Then train the whole thing, include the convnet and SANet, end-to-end. And this actually works. We are actually able to extend to learn how to solve the pictorial Sudoku. Specifically, we get the right answer on about 63% of puzzles, but to be clear, for a correct answer to occur, we need to get all our digit classification right, and the SANet layer has to get all the missing cells correct. Accounting for a probability of incorrect output from a convnet, this 63% accuracy actually translates to the SANet getting 85% of accuracy on the problem that the convnet correctly classified. The code for all these experiments is available at GitHub, and further, you can play online with Google Colab using the above QR code. To conclude, in this talk, we present SANet, the first differentiable smooth MACSET solver, as a layer. This layer can be integrated into a deep learning system as a layer whenever you think a neuron should be subject to certain logical constraints, but you don't know about those constraints are. A deep network constructed in this fashion is able to learn both the constraint and the solution solely from examples. And there are many possible extensions of this work. For example, imagine that you have some non-rules and not the others. How do we incorporate the non-rule while learning the unknown ones? And as another example, our fast solution technique here assumes the generic SDP. But if you have some structure that you know about the MACSET SDP, like the temporal or sparsity pattern, maybe you could use this information to speed up your solution procedure. There are still a lot of possible applications to SANet. For more detail, please see our poster at the Pacific Ballroom, number 26. Thank you.
Hi, thanks for the talk. I was wondering how you choose which clauses to include. So in the example, you had this formula that had 3 clauses, and then you had a 3-by-3 clause matrix. But how do you know which clauses you should have there? Or do you just include all of them?
So in the SANet setting, we simply assume that the S is a parameter matrix, and we will learn it all. We can set the number of possible clauses, and that is like a number of hidden layers. Did that answer your question?
So I'm asking like how you choose V2 and V1 or not V2 and V2 or not V3. Like how do you know that those are the clauses that you want to be looking at?
Let's look at the layer here. Okay, the full picture of the layer. So for solving the Sudoku puzzle, we are only given the example of unsolved and solved puzzles, not the rules. So we do not have any constraint about rules. We just say that there might be like 200 or 300 rules, and we set the dimension of the S matrix and let the system to learn it automatically.
So I understand, I think, more or less how you learn the S matrix, but the question is about like the semantics of the S matrix, right? Because each row, or I guess, each column of the S matrix is going to represent something about a given clause, but which clause? how do we know which clause?
There will be a mixture of clause in the S matrix, actually. So after you learn the S, you can actually not separate the original clause. If you want to separate that, you need to use other method. So please come to our professor. We can try that offline.
All right, thanks.
So one question about the implicit function theorem that you used. It has some conditions under which that it can give you differentiability. Are those conditions always satisfied for this problem?
Yes. Let me see. Do you mean that the Jacobian need to be invertible?
Yes, yes. The Jacobian has to be invertible for this to give you differentiability.
The Jacobian here will be locally invertible.
Okay.
And actually, in the solution process, we might add a diagonal parameter to increase the invertibility of the Jacobian matrix.
I see, I see. So it might not be invertible, but you're trying to. Okay, thank you.
Okay, so let's thank the speaker again, and congratulations. Okay, so the next talk is area attention. And the authors are Yang Li, Lucas Kaiser, and Sammy Benjo, and CC.
Thanks for the introduction. I'm Yang Li, so I'm going to talk to you about area attention. So this is a joint work with my colleague Lucas Kaiser, Sammy Benjo, and CC at Google Research. So as many of us know, neural attentional mechanisms allow a model to focus on specific information, which have significantly boosted the accuracy of a range of deep learning models. For example, in machine translation, a model can often decode better at each step by referring back to a specific token in the source settings. Similarly, in image captioning, we often see better captioning quality by allowing the model to focus on specific regions in the image. So rather than having the attention mechanism just as an add-on component, so architectures that are solely based on attention mechanisms, such as a transformer, have achieved state-of-the-art results on many deep learning tasks. So while attention mechanisms have played a central role in deep learning tasks, they are limited in the way that the unit of attention is predetermined rather than learned. For example, a model has to attend to a predefined token in a sequence problem or fix the image cell in image understanding task. So our goal for this research is to enable the model to attend to information at varying granularities. So in other words, we want the unit of attention to be learned rather than predetermined. So intuitively, we want to give the model the option to attend to a meaningful span of tokens for a sequence problem or a collection of cells that constitute an object for image problems, rather than being limited to individual cells or tokens. So to this end, we propose area attention. It's a general mechanism for a model to attend the information, to attend to a collection of items that are structurally adjacent. So if the overall collection, which we refer to as a memory, has a one-dimensional structure, the areas represent possible spans in a sequence of tokens. In a two-dimensional case, the areas represent also all possible regions in the memory. So as we can see here, the unit of attention is dynamically formed based on the learned coherence of structurally adjacent items. Because each area can aggregate a varying number of items, the unit of attention is actually determined from learning from the data rather than So based on this definition of attention, we can have a rich set of features to represent each area, such as the mean and the standard deviation of all the vectors in each area, as well as the shape of each area. So these features actually allow the model to potentially attend to more relevant information. So we have evaluated area attention on a range of deep learning tasks, which showed significant improvements on architectures such as a transformer and LSTM. Importantly, you don't need additional parameters to achieve the accuracy improvements. So if you're interested in the work, come to our post session. Thank you.
So the next talk is the Evolved Transformer by David So, Chen Yang, and Kwok Lee.
Hello, I'm David, and today I'm here to present the Evolved Transformer. This is work I did as part of Google Brain with Chen Liang and Kwok Lee. So the motivation for this work came from two primary observations. The first is the rise in popularity of feed-forward or non-recurrent sequence models such as the transformer. And the second is that in the computer vision space, neural architecture search can now produce models that outperform those designed by humans. And so the question that we wanted to ask was, can we apply the same type of neural architecture search to find better feed-forward sequence models for the first time? And to do this, we decided to employ evolution because it's simple and easy to tune and has done very well in the computer vision space, creating state-of-the-art models for tasks like ImageNet. However, in applying evolutionary NAS to the sequence space, we ran into several obstacles. For example, we designed a new search space that incorporates the strengths of the best feed-forward sequence architectures, but this space was a lot larger and less well-tuned than the one used in the vision space, from which random sampling also produces good architectures. Additionally, the task that we train on, WMT English-German translation, is more computationally expensive than the task used in the vision domain, CFAR10. So to overcome these compute problems, we augmented the evolutionary NAS method in two ways. The first is that we introduced warm starting. So previous NAS methods have started from random initializations, but we found that this was quite wasteful. And then actually, if you start your search from a known good architecture, in our case, the transformer, you can start finding better models faster, as well as ground the search in a part of the space that you have more confidence in terms of finding a better model. The second method we use is one that we developed ourselves called progressive dynamic hurdles. In short, what we do is establish what we call hurdles using mean population fitness at different train steps. And then when we're training a candidate model to evaluate it for fitness, we compare it to these hurdles, and if it's performing worse than the hurdles, then we just end its training right there and save all that compute. And that's what you're seeing in this figure on the right. The lines represent the hurdle values, and the dots beneath those lines represent the models that never got the full amount of training, and that's compute that we saved. So in our setup, this saved us roughly 75% of our compute. So running this evolutionary NAS with these methods, we found a model that we call the evolved transformer because we used evolution to find it and because we seeded the initial population with the transformer. This is a comparison between the seeded model, the transformer, and our evolved transformer on the task we searched on, WMT English-German translation. As you can see, the evolved transformer shows improved performance versus the original transformer at all parameter sizes we tried, with the biggest gains coming at the smaller and medium sizes, which are closer to what we searched on. But even at the larger end of the spectrum, the evolved transformer was able to outperform the biggest trained transformer with roughly 40% less parameters, and that's what's shown in the green circles on the left. Comparing to other results in the literature, the evolved transformer was able to reach state-of-the-art performance on this task, English-German translation, but we also cared about generalization. So we compared the two models on translation tasks that use other languages and found similar margins of improvement, as well as compared the decoders of both models on language modeling using LM1B and saw an improvement of roughly 2 perplexity. So what mutations took us from the transformer, which we warm started the search with, to the evolved transformer? This is the transformer decoder represented in our search space. And this is the evolved transformer. I don't have time to talk about all the details in terms of the differences, but the most salient feature of the evolved transformer is this branch convolution structure right here. This is just the decoder, but the encoder also developed a structure that looks very similar using convolution as well. And this is interesting to us because when we ran our search, we searched for the encoder and decoder simultaneously, but separately in the sense that they didn't share an encoding or architecture. So that both the encoder and decoder developed this same structure, I think speaks to its strength. Additionally, as you can see here, the evolved transformer is a hybrid, taking advantage of both self-attention and wide convolution. We've open sourced the search space that we used, as well as an implementation of the evolved transformer in the tensor library. So please consider giving the evolved transformer a try. And if you have any questions, we'll be presenting our work in the Pacific Ballroom this evening. We're poster number 28. Thank you very much.
The next talk is Jump Out, Improved Dropout for Deep Neural Networks with ReLUs.
Thanks for the introduction. I'm Shenjie Wang from University of Washington. I'm going to present our work on Jump Out, Improved Dropout for Deep Neural Networks with Rectified Linear Units. The dropout is a very powerful regularization technique for training DNNs. However, it has a few drawbacks. Firstly, the dropout encourages DNN to apply the same linear model to different data points, but it does not enforce the local smoothness of the network prediction in an effective way. And secondly, for a ReLU network, dropping the non-active neurons is setting zeros to zeros, which has no effects at all, but is still counting the dropout rate. And thirdly, dropout does not typically work very well with batch norm layers in practice, and is mainly due to the shift of the variance created by the dropout rescaling factor. In this work, we propose jump-out layers as an improvement over the dropout layers with 3 modifications to address the 3 issues above. In practice, jump-out has a significantly improved performance over dropout with almost no extra computational memory costs. So for the first jump-out modification, instead of applying a constant dropout rate, we sample the dropout rate from the positive part of a Gaussian distribution so that we have a decreasing probability for dropping more neurons. Our intuition is based on the geometry of a ReLU network with the purpose to encourage the local smoothness of the network predictions. So a deep ReLU network divides the input data space into convex polytopes, where each convex polytope has an associated local linear model, while two nearby linear models may be very different from each other. When applying dropout, we can think that instead of using the linear model of the current polytope, we use the linear model of some polytope that's nearby, and we enforce that one to also give the correct prediction for the current data point. However, if we are only using a constant dropout rate, we'll be only utilizing the linear models that are at around a fixed distance away in a ring-like region around the current polytope. While for jump-out, we are more probable to sample the linear models that are nearby than the ones that are farther away, and therefore the local smoothness of the network prediction is enforced. So for the second jump-out modification, we normalize the dropout rate by the portion of active neurons of the ReLU network. On the right, we plot the portion of active neurons across training epochs for different layers of a ReLU network. And we can see that such quantity may vary dramatically for different layers or for different training stages. Since dropping the non-active neurons has no effects at all, without the normalization, we may have some undesirable regularization effects. For example, for the case shown on the right, we'll be having a decreasing dropout regularization power as we're having fewer active neurons as the training progresses. Therefore, we needed the jump-out modification to have a better control over the regularization we want for different layers and for different training stages. For the third jump-out modification, we changed the scaling factor of dropout to the following quantity to account for both the changes, the mean of the variance between the training phase and the testing phase. The dropout rescaling factor is often applied during the training phase and set to 1 during the testing phase, as we are only using a portion of the network for training while we're using the entire network for prediction. However, such rescaling factor can only account for the changes in the mean of the output, but not for the variance. And in fact, there's no single rescaling factor that can keep both the mean and the variance unchanged. So empirically, from the two plots shown below, where the blue lines correspond to the original dropout rescaling factor, which can be almost perfect for the mean changes, but can be quite off for the variance. While the gray lines, which is the jump-out rescaling factor, has nice trade-offs for both the changes, the mean and the variance, and therefore it can synergize much better with special norm layers in practice. And here we present our results. On multiple data sets, jump-out has an improved performance of dropout, and from the training curve below, we can see that the jump-out consistently outperforms dropout across training epochs, and we can often get a much higher accuracy much earlier during training. That's all, thank you. If you have any questions or you want to know more details, please come to our poster session.
Okay, so the next talk is stochastic deep networks.
Hi, I'm Gwendoline, and I'll be talking about my work on stochastic deep networks, which is jointly done with Gabriel Perret and Marco Couturier. So we start from the observation that in biology or chemistry, it's sometimes not recommended to follow individual cells over time due to practical issues. Similarly, in other fields, it's not always feasible or advisable to follow populations at an individual level over time due to experimental costs or privacy concerns, for instance, gas or crowds. So we argue that in such settings, densities are the right object to perform learning tasks on. So we introduce a pipeline for dealing with probability distributions or equivalently random vectors in machine learning tasks. And that entails redefining the notion of layer of a deep net. So we call this new layer an elementary block, and we define it as follows. To some input random vector, we associate the expectation over an IID copy of the input of some function f of the input and its copy. This output can either be deterministic, which is useful in classification and or encoding, or random for dynamics or generative nets, for instance. In the discrete case, where the input is based on a sample x1, xn, the output also follows a discrete law with such new positions based on pairwise interactions of the input. This notion of layer entails the choice of some function f which we can choose as standardly done in neural networks, a linear function followed by a nonlinearity. Such a layer allows to output a deterministic vector, which is a summary statistic of the input, if f only depends on its second argument. And on the other hand, we retrieve a classical notion of a local warping of the input, if f only depends on its first argument. So such layers can be stacked to form deep architectures for different purposes. In the discriminative case, for instance, we expected as output a vector scores per class, for instance. So ft will only depend on its second argument. In the generative case, we adapt the variational autoencoder setting by considering each input which have both a deterministic part, which is the encoding, and a random part. And in dynamics, both the input and output are random. So we obtain the nice property that theoretically 3 blocks are enough in order to approximate a continuous function that takes a random vector and outputs another one, arbitrarily close, as long as some noise is injected in the process. And finally, we use this notion of layer in different applicative settings, so classification, generation, and dynamics prediction, where we use different appropriate loss functions with automatic differentiation for learning. We treated each input as a discrete distribution, so namely a point cloud with varying mass attributed to each point. And we found that 2 blocks were enough to retrieve state-of-the-art accuracies on MNIST and ModelNet 40, again treated as point clouds, and also satisfactorily generated point cloud digits. And as for dynamics, we used a predictive model that describes the dynamics of groups of fish or birds, for instance, namely a flocking model. And we predicted the limit distribution of a random number of such groups with varying initial settings. So what we have done is introduce a new formalism for deep architectures dealing with random vectors, which is able to cope with both probability distributions and deterministic picture vectors. We have provided instantiation of such networks and detailed their approximation abilities. And as for perspectives, a few things will be interesting to look into. For instance, investigate how such networks can cope with invariances, for instance. And please come by my poster tonight if you want to discuss this further. Thank you.
So this is the end of the talk, so let's start a break. Thank you.